In this video, we're going to go over the simulator node. This is where all of the operating conditions for the simulation are set for the cell which we made up here in the designer section. Let's take a look at the inputs. The first tab is the control parameters tab. The time step input determines the relative time step used in the simulation. Autoline will automatically adjust the time step to be inversely proportional to the applied current. For example, if the applied current is 10C, the time step will be 0.1 seconds under that condition. If, on the other hand, you set it to 0.5C, the time step will be 2 seconds, and so on and so forth. The output frequency determines how often the output data is written to each file. For example, if the output frequency is set to 50, the simulation data will be written every 50 time steps. Moving on to the mesh number, these inputs control the size of the electrochemical mesh used in the simulation. Moving up to operating conditions here, this is where you define the load profile for each simulation. If you click here in this drop-down menu, you can see all the available options. Here, CC means constant current, where you simply type in the value and it'll either charge or discharge at that value. Right below it is C rate, which is exactly the same as constant current, except it's normalized against the capacity of the cell which you designed. CCCV is just a constant current, constant voltage charging protocol. CP is for constant power. CR is for constant resistance, which can be used to simulate external shorts in the battery. And UDLP stands for User Defined Load Profile, which is really useful for inputting pulse profiles or real-world drive cycle data. The bottom three options are used in the degradation model, which will be covered in another video. For this case, we'll select UDLP. We can use the Browse button to input the file that you'd like to use. Here you can also define the upper and lower cutoff voltages for each simulation. Moving on to the Initial Conditions tab, here you can input the initial cell temperature, the initial voltage at 100% state of charge, and the initial state of charge that you'd like to use for the simulation. Moving on to the Butler-Volmer equation tab, this is where all the parameters for the electrode reactions as described by the Butler-Volmer equation are contained. We'll take a look at the negative electrode for all the inputs, and you can see all of the parameters available which are used in the Butler-Volmer equation. So a few important notes here. If we take a look at the OCP value here, it reads database. This means that during the simulation, Autoline will read the input directly from the built-in materials database for whichever material is selected in the designer tab. If we click on the value here, we have the option to choose what's called a UDF, which stands for User Defined Function. This allows you to input your own custom OCP curve from your own experimental data or a function taken from literature. You can see this is also an input for the exchange current density as well as the entropic heat term. All the inputs are the same for the positive electrode, and again we see the options for the database or the UDF input. Moving on to the Bruggeman Exponents tab, this is where the tortuosity of the electrodes is defined using the standard Bruggeman relationship. In the Electrolyte Concentration tab, you can define the diffusion coefficient in the electrolyte. Again, you have the option for the database or the UDF inputs. In the solid state diffusion, you can define the diffusion coefficient in the negative and positive particles. In the Electrolyte Potential tab, you can define the ionic conductivity of the electrolyte, and again you have the option for the database or the UDF. In the solid phase potential, you can define the solid phase conductivity for each electrode, as well as the contact resistance inside the electrodes. This is a lumped parameter which encapsulates all sources of electrical resistance in each electrode, including the contact resistance between the current collector and electrode, the separator and electrode, etc., etc. In the heat transfer node, you have the option to turn the thermal model on or off. Off means you're running an isothermal simulation. You can also define the ambient temperature, the cell-specific heat, and the convective heat transfer coefficient. And last but not least, we have the degradation node, which has each degradation model separated into each electrode, with the option to toggle each model on or off. This allows you to run simulations while isolating individual degradation models for each electrode. And that's it. So once you're done setting up all these parameters, you're ready to run your simulation. Check out our other videos to learn how to get things running and then post-process all of your data when the simulation's done. Thanks for watching, and we'll see you next time.